In order to fully understand the story of black holes, it's important that we start at the beginning. To know why black holes are formed, we must first understand why the objects that form black holes are formed. As stated in the introduction to this module, stellar mass black holes are one of the two possible products of violent explosions of high-mass stars which occur at the end of the star's life. These explosions, called Type II or core collapse supernovae, occur in stars at least 8 times more massive than our Sun. When a massive star experiences a supernova event, the amount of energy released is on the order of 10 to the 46 joules. That's enough energy to last the Sun at its present rate of energy output, 825 billion years. For reference, our solar system, along with our Sun, has existed for just 5 billion years. The universe has existed for a mere 13.8 billion years. Clearly, that is a huge amount of energy. If you're anything like me, right now you'd have a ton of questions, starting with, how is it that some stars meet such violent ends? How do stars even form in the first place? Technically speaking, what is a star? Let's begin by answering the simplest of those questions, what is a star? Simply put, a star is a big ball of gas which is gravitationally bound and dense and hot enough to sustain a nuclear fusion reaction at its core. Our Sun is one such object. It, like all of the main sequence stars, produces energy by fusing hydrogen into helium in its core. Most stars are spherical, or if they happen to rotate quite quickly, we call them oblate spheroidal because they're slightly squished. So now that we have a working definition of what a star is, let's move on to the next question. How do stars form? Stars form in clouds of gas and dust which are particularly cold and dense, at least by interstellar standards. These regions are known as molecular clouds because their temperatures are low enough to allow molecules to form. Molecular clouds are just one component of all the gas and dust in the space between stars, known as the interstellar medium, or ISM. What distinguishes molecular clouds from other gas and dust in the ISM is the effect gravity has on them. Molecular clouds are cold, between 10 and 30 Kelvin, and dense, several hundred molecules per cubic centimeter, meaning there are plenty of particles in close proximity to each other and at the same time relatively little gas pressure. These two conditions are each very important for star formation, as they allow the inward force of gravity to overpower the outward force of the gas pressure and initiate the collapse of the cloud. As the cloud contracts, it releases gravitational potential energy. This energy is converted into thermal energy, which in turn increases the pressure within the gas. Without some way of removing thermal energy, the gas pressure would build and eventually stop contraction of the cloud altogether, prior to the formation of a star. What is needed then is a way to get energy out. A way to get energy out so that gravity still has the advantage and contraction can continue. Thermal energy manifests itself in the random motions and frequent collisions of molecules. Collisions between molecules in the gas can excite the molecules, allowing them to produce light that can escape the cloud. And so without a buildup of thermal energy and gas pressure, the cloud is free to continue contracting. However, as contraction continues, the central region within the cloud eventually becomes so dense that light emitted by molecules and by dust grains has a hard time escaping. More particles present in a given volume of the cloud means an increased likelihood of absorption of the light by other molecules and subsequent conversion of that energy back into thermal energy. Over time, the cloud's increasing density will result in nearly all of the radiation being trapped within the central region of the cloud. When this radiation trapping occurs, pressure in the central region increases to a level which slows the rate of contraction. This is the formation of a protostar. When observed through telescopes, protostars look much the same as regular stars, in that they have similar luminosities and surface temperatures. The difference lies underneath, as protostars are not yet hot enough to sustain fusion reactions. In order to become hot enough to sustain fusion, protostars must gather more material and squish it. Material surrounding the protostar feeds down onto it, and at the same time, gravity continues to slowly squish this protostellar material into smaller and smaller regions. As the protostar contracts and heats, the fusion rate increases, and the heat generated by these nuclear reactions provides a pressure force that slows the contraction caused by gravity. When the core temperature of the protostar reaches about 1,000,000 Kelvin, the winds generated at the protostar's surface blow the surrounding gas and dust away, ending the accretion phase. Now without its source of additional material, the protostar continues to slowly contract and heat until the core temperature reaches 10 million Kelvin, at which point fusion becomes stable and we have a star. Fusion rates become stable because the forces in the interior of the star become balanced. Nuclear reaction rates are now high enough that they produce the necessary heat and pressure to prevent the star from collapsing further due to gravity. When the gravity and gas pressure forces are in balance, we call this state hydrostatic equilibrium. The net force on material within the star is zero. The star can remain stable in this state for billions of years. Our Sun is currently about 5 billion years old and in a state of hydrostatic equilibrium. It will remain in this stable state for another 5 billion years. It's time again for us to confess about a lie of omission we've been telling. Until this point, we've been considering a scenario of star formation which isn't perfectly realistic. We've been considering a single cloud in isolation, when in reality, individual sites of star formation are often influenced by other nearby sites of formation and by nearby newborn stars. In truth, large molecular clouds fragment as they contract into several smaller cloud cores, and from these, one or more stars form. Often what we have is several neighboring sites, potentially each producing several stars. And then there's the matter of those additional dynamical aspects we also forgot to mention. More than just two forces are present in molecular clouds as they contract. In addition to gravity and gas pressure, magnetic fields affect molecular clouds by slowing their contraction. Magnetic fields cause particles in the cloud to move in such a way that they exert a friction on each other, hindering motion within the gas and helping to prop up the cloud against gravity. Turbulence also plays an important role. Gas clumps moving relative to each other at large speeds act to shear the cloud apart rather than facilitate the cloud's contraction. In the later stages of star formation, material surrounding the protostar will coalesce into a disk, and the protostar itself will eject material from the system via large jets. So, suffice to say, star formation is very complex. But star formation is also incredibly commonplace. Several stars finish forming in our galaxy every year, and in total, our galaxy contains roughly 100 billion stars. And the key to our final question, how do some stars meet such violent ends, lies in the variety of stars which result from the formation scenario.